Very.
Yeah.
Good morning, everyone. So today is our new topic, topic 9. So
What's the
title is
problem?
general purpose input output.
What's
No,
the problem?
I think
Yeah.
Prof remove his WebEx link
So
from
I've updated the notes. So
e-learning.
your
So
old
it's
notes is
but
obsolete.
yeah.
I've added some things
I
last
think I
night.
cannot hear you.
Actually, for
Yeah.
2 days I've been working on this,
No,
and
it's okay.
I slept 2 o'clock this morning. All right. So first section is overview of input-output programming. So this one is a little bit of repeat from, or it's the same from last few previous semesters. So a little bit optimized. Okay. So so why is input-output programming different than normal programming? Okay, quote unquote. Okay. First is input-output has speed issues. Okay. Mainly is because I/O devices I/O devices operate at different speeds than the CPU. Yeah, I see some comment here. Okay, let me see. Let me pause for a while. I can't hear you because of wrong configuration on my side. Okay, so just to be clear, I put it on the chat. So anything, we just message here lah. Okay, so if during break time, I'll try to fix it. Okay, anyway, so let's continue. So why is I/O programming different? Mainly is because of the speed issue. It's because the I/O devices operate at different speeds. Most I/O is slow, okay, but not all. So if the input output is slow, the CPU must wait for the input output device. And some input output device are faster than the CPU. So if it's very fast, then you have to use direct memory access to avoid dropping data. But what that means is that you cannot take data from the device into the processor and store the data to memory. That is too slow. Okay, what we need to do is to have the device send data directly to memory. That's called direct memory access. But for fast devices, you have to do that. So this is quite a complex operation that we will not cover in this semester. All right. So another thing that's different is that I/O devices must be accessed through peripheral registers. Okay, so you cannot go directly to a device and ask for data. You have to go through a peripheral register inside the microcontroller. Okay, so inside our microcontroller, we have the CPU and we have a lot of peripheral registers which are then connected to the I/O device. So we are going to learn how to access the peripheral registers. Okay, and then the third way I/O is different than memory is that I/O data has many different formats. Okay, it's not just like 8-bit, 16-bit, 32-bit. That's simple. Okay, but I/O data has many different formats such as parallel data, we have serial data, we have digital data, we have analog data, and then there's also data that come in burst. Okay, it's not piece by piece, but when it comes in burst, so you must grab the data very quickly. Anyway, the simplest form of input output is general purpose input output, which is what's covered in this chapter. Right. Next, when we are going to access input output, there's three main programming strategies. First is program I/O, and then we have interrupt driven, and then we have direct memory access. Okay, so program I/O is the simplest, and we will cover only this method in this topic, this module. Okay, and then we have interrupt driven I/O. Is efficient for most cases. Okay, so in the interrupt chapter, we'll look at it briefly, and then we also have direct memory access, which is required for high-speed block-based devices. Okay, so this one maybe it's not covered, but it's not impossible to do. You just look at some tutorials. Uh, should be okay, I think, after some experimentation. All right. So for program I/O, as I mentioned just now, um, this is the most suitable for slow devices. Okay. So we have a loop here. Okay. So we have the uh, in this kind of output in programming, the CPU is faster than the device. So the CPU must monitor the device constantly. So we have a wait loop. Okay, so this is a wait loop, or sometimes called the busy loop or spin loop. Okay, so this is a wait loop. Okay, so the processor will stay in this loop until the device is ready to transfer. So what happens is, if your processor is very fast, like our uh, STM, which is like 180 megahertz, and you're only waiting for a human to key in something on the keyboard, you will be waiting for millions of cycles. Okay, so this loop will go around and round for millions of cycles before you do anything useful. So basically, the processor is busy waiting. Okay, it's busy, but it's only waiting, not doing anything. And when the device is ready, the CPU will read from the device, and then the device is then sent to memory lah. Okay, and then the procedure continues. Okay, so simple but not efficient. Okay, the next method is by using interrupt driven, where the the peripheral register informs the computer when the device is ready to transfer using the interrupt function of the processor. So when the processor when the CPU is running a program, it does not check the flag like just now. Okay, that when the device is ready, there's a flag saying the device is ready. So the program, what you can refer to the flow chart here. Okay, so first you issue the command to the I/O module, and then the CPU can do something else. And then between this part, okay, the one that I circle, that one is actually nothing to do with the I/O, because the CPU is now with something else. So this loop is only for the I/O, but the CPU itself, first it sends command to the I/O device, and then the CPU does something else. So when the I/O device is ready, it will interrupt the processor, and the processor can check the flag and read the data lah. So basically, the CPU is not waiting for the device to be ready. When the device is ready, it will tell the processor to get the data. So let's say your system is very simple. You can still do this, but there's nothing else to do, right? So from the moment you send command to the device, the processor can do something, but actually there's nothing to do, because our system is so simple. There's nothing to do actually. So what you can do is send a command to the I/O device and sleep. Okay, so the processor can sleep and save power. And when the device is ready, it can give an interrupt and wake up the processor. So interrupt-driven I/O is also usable to save power, not just to do multitasking or save processor cycles, but you can turn off power when there's no input-output taking place. All right, and then lastly, we have the direct memory access. Okay, so in direct memory access, okay, you can look at the flowchart on the right here. Okay, the processor send data to the device, okay, so that the device can do a direct memory access, and then when the device is ready, it can inform the processor that the transfer is complete. Okay, so like the interrupt for the DMA, the processor can also do something while the input output is taking place. But the advantage of the MA is that the processor does not have to handle the data transfer. Okay. If you look at this diagram, okay, without the MA, you read data from, let's say I want to send data outside lah. Okay, so I want to send data outside from memory. I get to transfer to the CPU, and then from the CPU I send to the device. So there's two steps. If I want to read, I have to read from the device, and then I store into the memory. Okay, so that's two steps. But if the device is very fast, even the CPU cannot handle the data transfer. So you just let the device take over the data bus and the address bus. Okay, so basically the DMA device control or take over the system bus. Okay, so now we have not only the CPU being the master of the bus, but the DMA device or the IO device become the master and do the transfer. So now you have master number one, master number two. Okay, the first one no master lah because only the CPU can control the bus. But if you have DMA, then you have master number one, master number two. So if you are uh, doing this, the DMA, the CPU can do something else, or it can sleep, okay, like just now, or for a very busy system, both CPU and the DMA can access the system bus using bus sharing. Okay, but even the system bus, if you use a bus is a shared. Okay, you know, a bus is a shared resource. So if the processor is using the bus, the DMA device cannot use the bus, or vice versa. So in the STM32, they don't use a bus, but they use a cross bus switch, which is even better lah. Because on the cross bus switch, you can perform parallel transfer. So on the STM32 that we have, actually is more advanced than what we see here. And the DMA is more efficient because there's no waiting. All right, so that's the overview of input-output programming lah. And then we go to the next section, more details on the STM32 architecture. Okay, we have seen this before, but now there's some added details that are relevant for I/O. Just now, before that, we just study in general, but now we go to the I/O relevant stuff lah. Okay, so before that, something that we missed before, STM32 naming convention lah, like the one that you. So now let's say you have your nucleo board. It's STM32F446RET6. What does it mean? Okay, so that means STM32 is the 32-bit MCU or the ARM. F is the foundation field series, but you can also see that there's also a low power and wireless versions. Okay, and then the 446 here is actually each digit has a meaning, but basically 446 is a number lah. Okay, so 446 is a number, but I think 4 is for the Cortex 4 lah. There's actually a longer list, but from this particular diagram, I don't have this list. So this list can be a bit longer. Okay, there's more details there. But it doesn't matter that much. We know that 446 is going to be different than 411 or 401. And then there's the R here. Okay, the R here is for the pin count. Okay, so for ours, for the nucleo board, we have 64 pins. So R here stands for 64 pin chip. Actually, the STM32 has other packages also that have more pins. So the code here is not necessarily R. And then E here is for the flash size. So E means we have 512 kilobyte of memory. And then T here is for plastic packaging, and 6 is the it's the temperature range. This is the cheapest version, plastic. So starts with it ends with 6. Okay. So at least now I know what that means, what all the characters mean. And then we have there's several versions of STM446. So the one that we use is actually the cheapest one lah. This one, not the cheapest lah. I think this one, the bottom one should be cheaper. Okay? But cheaper in terms of horizontally is the cheapest. Okay, if you look horizontally, okay, you can see that there's also 81 pin version, 100 pin version, and 144 pin version. So probably the die inside is still the same, but because the packaging is smaller, so not all the pins are available. So many I/O ports are not available. So on the one that we have port A, B up to A, B, C, D only for the I/O. But for the big versions here, it can go up to H. Okay, so bigger, but still internally is the same processor. And as we know, the STM32 can run up to 180 MHz. This is actually faster than, much faster than the original BMPC, which was 4.77 MHz only. That's the original granddaddy of processors, of personal computer. It's much faster. And then, for most microcontroller, the main memory is flash memory. Okay, that's the cheapest or the most cost effective now, but it's very slow. So because of the difference in the speed between the processor and the memory, so ST Micro, they did some fancy tricks lah, but they don't use cache because cache is expensive. All right, so among the things that they add is the phase lock loop, the memory accelerator, the switching matrix, and the complex system clock. Okay, so very complex, huh? So if you look at the diagram copied from the datasheet, that's the clock circuit. So on the STM32, we have 4 types of clocks. First is the high-speed internal oscillator. Okay, so this one is 60 MHz. And then there's a phase lock loop, which can be driven by external crystal or the HSI just now. All right, so if you want the maximum 180 MHz, you have to use the external 8 MHz. So that means for our system, we may never get 180 because on the Nucleo that we have, it uses the HSI lah. So it can go up to 168, but I think that's very good enough. And then from the phase lock loop, it will generate the 48 MHz for you to use for USB and I2S. And then there's also the high-speed external oscillator. And lastly, there's the low-speed internal oscillator. There's an internal, okay, inside the chip, there's a RC oscillator. This is used to run the watchdog timer. So watchdog timer, maybe we have time, maybe not. Time to cover what is a watchdog timer. But for now, let's say that the watchdog timer is a timer that looks after the system. So if the system crash, the watchdog timer can restart. It can somehow detect stuck microcontroller and reset the processor. So this is quite useful if you want to have a reliable system that can restart itself. So the Nucleo uses the internal oscillator here, okay, the one here, okay. So this is the one that we have. If you use Discovery, it uses the HSE oscillator, okay. So then you can get 180 for Discovery board. But of course, the Discovery board costs a little bit, right? And then to run all the peripherals, okay, we need also some clock which are derived from all these other clocks. Okay, so on the thumb, there's two big types of buses. One is the AHB, Advanced High Speed Bus, and the other one is Advanced Peripheral Bus. Okay, so the high speed bus is normally used to connect to flash memory, and the peripheral bus is used to connect to low speed peripherals or lower speed peripheral. Okay, in this case, we can see that high speed here is 90 and the low speed is 45, and depending on the device they allocate lah. So ST, the maker of STM32, they allocate which device goes to APB1 or APB2. Okay, so on reset, the system clock is internal 60 megahertz, and so that means all the devices and the processor itself all run at 60 megahertz. So that's the default. So if you don't change anything, the processor is actually running at 60 megahertz, and even that is not very accurate because it uses RC oscillator, not a crystal. So actually it's easy because all the buses run at the same speed. The CPU, the high speed bus, the peripheral bus all run at the same speed. So interfacing wise, not that much problem because they all run at the same speed. But of course, it's not the maximum speed. Okay, so internally the Cortex can run at 180, but you must use the VCO. Okay, going back here, you must use the VCO and phase lock loop and so on lah. So you must use the 8 megahertz crystal, which we don't have on the Nucleo. But if you have the crystal, okay, then we can see that the VCO first what it does is that it will divide by 8. Okay, so they divide 8 megahertz by 8, so we have 1 megahertz, and then in the typical PLL there's something called a phase comparator. Okay, we'll check the phase, and then due to the error, okay, there's an error here, so it can generate a higher frequency than 1 megahertz. So from 1 megahertz it can generate 180 megahertz. Okay, that's the job of the VCO here in the PLL. Okay, so anytime you see PLL, you have to appreciate lah. Okay, so it's analog device, it's an analog component which can generate a higher frequency than the original oscillator. So when you look at the oscillator 8 megahertz, previously lah on 8-bit microcontroller, that's the speed that we run, or maybe lower. Maybe from 8 megahertz, it divide by 4, so eventually your final running speed for the microcontroller is only 1 megahertz. But on the STM32, from 8 can go up to 180. I think that's amazing to me because as a digital person, I don't know much about analog. So this thing is analog. So you have to appreciate what the analog people are doing. All right, and then here we have the art accelerator. What is it? So cache memory is not used on the STM32 because it's complex. So complex means also expensive or use power or whatever lah. So STM32 uses another method to make it simpler and probably lower cost and lower power. So what happens is it divides the flash memory into 128-bit words. So many 128-bit words. So each access to memory will grab 8 16-bit instructions lah. So 8 times 16 equal 128 lah. Okay, we know that. Okay. So that means even though you only need one instruction, it will grab 8. So maybe you will only need one, but most probably it will use all 8. So it's the same way cache memory works. Okay, so cache memory also works similarly. Okay, grab one and then grab a few other pieces of data at the same time. Okay, so most probably you will also use the following instructions because when you run a software, you have instruction like this. When you run code, normally you run sequentially. So let's say I have instruction 1, 2, 3 up to instruction 8. If you don't have a loop, then you will execute all that. So that means from the moment you grab the first instruction, you already have the other remaining instruction in the sequence. So you already have 8 instructions. So that means you don't need to spend any more time to read the remaining 7 instructions in sequence. So that's how it saves time. But if there's a conditional branch, like say I have a BNE here or BL whatever branch, so it will jump somewhere, jump down here or jump back. So that means the data here, the data that was just fetched, it will not be used. So that means uh, you have to fetch somewhere else. Okay, so if you have a branch, then of course it have to fetch. Okay, let's say I branch here, I branch another place. From this sequence, I branched another place, so it will grab another sequence of 8 instructions. So it will have like a cache. It will store this new list of instructions in a buffer. So it will store somewhere here lah. Okay. So basically, it looks like it is a cache. Okay? It's just not called a cache. Okay? Because when you have a cache, you will store or you will predict what will be used later. So you will grab it, hoping that you will use it later. So this is actually what happens, but it's just not called a cache. All right. So basically, it will save all these branch instructions at the target locations, and we have that's why we have two buffers here. Okay. And then we have the branch management here. So this also uh, happens in cache memory. We have branch prediction and branch management. So it's like a cache, but only a cache. Okay, and then we have also the crossbar switch that I mentioned just now. Okay, let's jump ahead. Okay, this one. Okay, so the uh, processor have many potential bus masters and many slaves. Right? Okay, so we have at least 5 masters. Okay, at least 5 masters. We have I bus, D bus, S bus. Okay, so I bus is used to fetch instruction. The D bus is used to load literal. That means this is like a constants inside uh, the data memory. And then we have another master for accessing data in the peripheral or RAM area. And then they also have DMA. Of course, DMA can become the bus master. I mentioned this now. Don't forget that. So at least 5 potential bus masters. So if you use a bus, okay, you will need to wait lah, because in a bus, the lines are all shared. So if anyone is using, the other 4 will have to wait. So in the STM32, they use a crossbar. So if you go Google after this, what is a crossbar switch? It's a complex circuit which enable data to be accessed simultaneously, okay, from multiple masters or almost simultaneously. So in this case, they have arbitration. That means it's not simultaneous lah. So let's say 2 master want to use the same to access the data at the same time. So there's a way to decide which one have access to the resource. So that's called arbitration. So arbitration serves the purpose of resolving who have access to the data when 2 or more devices want to access the same data at the same time. So they use what's called the round robin algorithm to decide. So this is actually a complex thing to have in a very cheap microcontroller. Okay, so here we can see on top here all the bus master. Okay, the the cortex itself has three sources or 3 ways to access the bus, and then we have DMA, and then we have DMAs here, and then others lah. Okay, if you look here, these are the things that really requires high speed DMA. Ethernet very fast if implemented, and then USB also very fast, LCD also fast, but not sure this one is available on 446. I got this I think from 446 datasheet, but I didn't see this. Doesn't matter lah. Still from the same family. That means there are chips inside the STM32 family that can handle Ethernet and USB natively. Okay, so anyway, on the right side here are the slaves. Okay, so the slaves, they are just like respond or give data when requested. So let's say the processor want memory, want data. So let's see, is there a connection? Okay, now we have see this cross here. That means it can go here. Some don't have any connection. For example, the D bus. Okay, the D bus here can also only access uh, flash memory and static RAM, but it cannot access SRAM2, SRAM3, and so on because there's no connection here. Okay, no connection here. So it's not all to all. Okay, depending on what is the master and what is the slave, then the data transfer can take place. But DMA, you can see here, DMA2 can access almost everything. Okay, here, very powerful device, even more powerful than the ARM itself. Okay, so this is where is it lah. Okay, so let's say I want to access the GPIO. Okay, so the cortex will go through. Let me see here. I think the GPIO is AHB1. Okay, AHB1 is here lah. So GPIO will be here. AHB1. So it will go to AHB1. Okay, so go back here. So the processor has three ways. No, okay, only one. Must be through the S bus. Okay, must be through the S bus. So through the S bus, so that means go through here S bus, go through the matrix, go to the AHB bus, and do the GPIO port. That's how the data transfer is done. So all each device has different speed requirements, so they're not all connected. Okay, and then we can see here there's so many ports, right, on the 446, and on our small chip on the Nucleo, this one don't have. Okay, not connected. Okay, and if you go through this diagram, you can see there's other peripherals with different speeds like the camera. Okay, the camera has FIFO, so of course it's high speed, so it has to go through the AHB lah, HB2, and then where is APB? Oh, this is AHB high speed also. Then HB1 and HB2. I don't see APB somewhere. Okay, quick look to the back. Okay, AP1, APB1, and APB2. I don't see. Has to be there somewhere. It's okay lah. Let's go move on. Okay, so again our memory map. On this, our code area is this side. And then we have static RAM, and then we have bitband region. Okay, so make sure you know a little bit, you know what is bit bending, and then all our peripherals are here. Okay, so this is the most important part that we will need to do for I/O. This is the one. Okay, this area. All the rest you can skip for this chapter and for the 2-3 following chapters. This is the most important area for input output, because these are where the peripherals are located. Okay, so starting location 40 million. Alright, so sample list of I/O addresses, not complete, just a sample. Okay, so all start with 40 million, and then at the back, depending on the location. So for example, D2A have a different address than GPIO. So the one that we will cover, yeah, this is this one, and actually we'll jump this one is somehow related to GPIO, and then ADC some timer. Okay, only timer 2 is listed here, and timer 6. Okay, not all, and then we have interrupt controller, USART, and flash. So this is a sample list of eyewitnesses. Of course, there's more. That's why the datasheet is so thick. Okay, 9:50. So I take a very short break, and also I try to fix the sound. Okay, short break. Take a breather and try to fix the sound. Okay, so for you, you can take the time to download the slides. But Osman, can you say something? Test. I already disabled my 4K monitor. Anybody?
Test, 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 test.
Yeah, yeah, can. Now I can hear. Very soft, but can hear. Thanks. I think I need to buy some kind of speaker to the monitor lah. Because the HDMI cable routed the audio automatically to the monitor, but the monitor doesn't have any speaker. So that's why it's very quiet. Okay, should be okay now. Okay, I will put back the QR code. Okay, for my class, it's fine.
Prof. Munim, I don't know whether you realize or not, but I think you remove your WebEx link from the UTM e-learning webpage, so it's a bit difficult. I mean, like initially I had some trouble finding the link.
Oh, okay. Yeah, yeah, yeah. Okay, I'll do it. Sorry. It may be fixed, maybe not. You can test. So I changed, I put both links there, me and Dr. Usman. Okay, so problem solved, I think. Okay, let me see. I will share Dr. Usman's QR code for 1 or 2 minutes in case anybody want to scan. Okay, should be enough, huh? Okay, so let's resume. Share Acrobat. Right. So for this section, we will look at the deep I/O on the Nucleo and overview of I/O programming. We still have a long way to go. We have we have 70 slides, but we are doing okay. So 1/3 of the way now. Okay, so something that we have seen before. Okay, maybe no need to cover, but I'll just do it anyway. Yes, we have LDD1 somewhere here. Okay, LED1 is where? LED1 is, still I cannot see it, but I see LED2 here. Okay, and LD3.
LD1 is the right top, right? The white one.
Oh, this one. Oh, okay, all right. Okay, that's the, oh yeah, because it's on the ST link one. Okay, so the LD2 is the one that you can control lah. Okay. Then the LD3 is power. Okay, and then we have buttons, two buttons, B1, okay, B2. Okay, so the B2 is the reset, but the B1 we can play. We'll try to use it. Okay, so here is the connector pin out. The purple magenta-ish one is the Arduino. Okay, so you can see the Arduino is not symmetrical. Okay, shorter on the left side. So that's the Arduino, and then the blue one is the Morpho. So for uh, the Arduino doesn't have that many pins. So if you need more pins or you need to access to more signals, you have to use the header, the Morpho connector, and there are different gender. So this one is female, and this one is male. So make sure you have the right connector. So should be okay lah. Can access almost everything. So the pins on the Nucleo board, we have all pins from port A. So if you want to do interfacing, you can use port A. So where are port A? So port A 012, and then we have port A, where is it? Okay, we have 4, 5, 6, 7 here. Okay, 3 here. Okay, 8 there, 8 pins. And then we have 8, 9, 10, 11. Okay, so just count the count, just count. So we have all this, and then we have this. Okay, so that's all for port A. So port A is full, everything is there. Port B, we have PB0 to 10 only. So here is PB1012, PB10, and then we have PB12 to 15. Okay, this is one group. And then where else? Okay, it's here. Okay, for PB is not contiguous lah. Okay, 0, 1, 2 down here, 3, 4, 5, 6, 7 on top there. I think I'm missing 8 and 9. Um, okay, here, 8 and 9 here. And then we have 8 and 9. And then we have 10. And then 11 is not available, not even on the chip. So it's not on the chip, it's not on the Arduino. So PB11 is not there. So PB11 there's only 15 bits, and then for PC we have everything. So we have 16 bits for PC. So PC is there, and then we have PD2, only one pin. Where is it? Okay, here. Okay, there is PD2. Okay, so from port D only one pin, and then we have port H. Port H is here. It is port H. Okay, so we have E, F, G not taken out. E, F, G not available. So PA 13 and 14 not recommended to use. So should be avoided, but actually nothing to say we cannot. Okay, if you're not debugging, just use it. And then the user LED just now is connected to PA5, and that is pin. It's here. Okay, so this is LED. LED is connected here. Okay, and then push button is connected to PC13. So push button is here. So switch is here from the Arduino or the Nucleo board. We have already connected. We have used 2 pins commonly. Okay, so and then here is GPIO electrical diagram. Okay, so by default, all the pins will be in GPIO mode. And then here later we will see that we need to know what to do with this. Okay, so later on. Okay, so keep that in mind for later. Right, so as we've seen just now, PA5 is connected to LED, and then it uses 510 ohm resistor. Very funny value. And then the switch is connected to PC13, and the switch is here. And then there's also some resistors on top and the bottom, and also a capacitor here for debouncing. And also we can see that we have a crystal here for the low speed. Okay, so the low speed external, okay, low speed crystal, we have the 32 kilohertz crystal here. All right, so these are the main features. Okay, up to 16 IOs under one port, and then the output can be push-pull or open drain plus pull up or pull down. Okay, push-pull and pull up is different. Okay? Push-pull is not the same as pull up or pull down, and then it has open drain. And to use the port, the GPIO, you look for this register. So GPIO X, where X is the variable A to H, and then we can select the speed for each IO. For input, okay, for output, this is for output. Okay, for output we have a few states that we can select. For input also we can select. So there are some values that we can ignore, but if you want to do proper interfacing, you have to know what these are. Okay, and when you want to read data, okay, just now we have this register is to output data, ODR, output data register. For input, we use the input data register. If you want to set or reset and you don't want to handle the whole register, you can use the BSRR register, okay? Bit set reset register. And of course, you either use this or use this. The option is there for you. And then we can lock the bits using locking. Totally, I don't know why why do I want to do this? And then we have analog function, we can input data in analog. And then we can also have alternate function. That means all the pins can have some other function like timer or UI or UZ or SPI. So if you use all these alternate function, the GPIO function will be disabled. And we can do fast toggle capability. So that means you can toggle the output every 2 clock cycles. If your processor is 180, that means you can toggle at 90 megahertz. So the output will be like that lah, at 90 megahertz. So to do this, you have to know how to manipulate the clock. Because remember that by default, when you turn on the processor, it only goes to 16 megahertz. Okay. And then because of the alternate function, we use we have multiplexing so that each pin can have multiple functions. Okay, so if you want to use the GPIO, these are the registers that you have to know. Okay, so you any register with the GPIO in front, plus you have to put some character here. Actually, for this particular address, it's only A lah. Okay, I should not put X there. I should put A. But if I want to use if I want to use port B, so I will use GPIO B underscore mode register, and I will get a different address on the, so this is not totally correct. So this is all for port A, and then we have another register to enable the ports. If you don't enable if you don't use this register, this peripheral register, the GPIO is disabled. So the green ones, these are the minimum registers that you have to know for your final. The rest you can sort of skip lah, or you can read at but these are the required stuff that you have to know. This one you have to know. Okay, mode register, input data register, output data register, and the AHB enable clock. Okay, so this one will enable the peripherals on the AHB1 peripheral bus. All right, then we go to how to access. So once you know how to access the GPIO register, you can adapt the methods for any IO port. So for this chapter, we just learn how to use the GPIO register. So the first way is direct access to the address. Okay, it works. Okay, no problem. You can use this, but it's too easy to make an error because there's so many digits here. Okay, you must make sure the number is exactly what you see on this table lah. So let's say I want to access this register. So I have to make sure I copy paste lah. Normally I copy paste. Okay, 400 20010. So I copy that here. Okay, and then need to put some comment in case we make a mistake. So the comment here doesn't do anything, but you still need to comment if you use this. Because it's very easy to make a mistake. Alright, so right now, let's say I want to read data from the input data register. So I put this typecasting. Okay, so I will convert this number to a pointer, and I will read the data and put into the store into the value val. If I want to write, I just reverse lah. So then if I want to write, I cannot use the same register. I have to use the ODR register, different address. Okay, so different address. I'll refer back here, make sure. Okay, go back here, make sure same number. Okay, copy that number, put it here. So this one, you don't have to do any include files or anything. Just use this number. You can directly read from the port and write to the port, provided you enable the port first lah. Okay, so this method can also be adapted to assembler. Okay, so this one is the one I was was mentioning to Dr. Osman. Some new instruction I learned this morning. Okay, so let's say I want to access register location for. Okay, I want to input, right? So I want to access location for 00 to 0010. So I need to have this number into R0 if I want to use R0 as a pointer, right? So Before this, I would do what? I would do ADR R0 equal 0x 400 200 10. Can be done lah. But ADR is actually not, this is not an actual instruction. Okay, ADR is a pseudo instruction. The assembler will convert that to a few moves sometimes. Okay, so if you know how to use this new instruction that I just found today, then you can do it manually lah. So you don't have to use ADR. Now you go really down to the machine, because you're not using a pseudo instruction, but you're using a real instruction. So what I do now is I will put I use move W. Okay, move W. What happen is I will uh, put number here lah. So move W will take a 16-bit number to the lower part of R0. So 16-bit here. Okay. Remember that you cannot put the constant here cannot be too big. Okay, here we have a very big constant which cannot fit into it cannot fit into the same instruction. That's why the instruction has to be broken up into this pseudo instruction is broken up into a few instructions. But if you have only 16 bits, so there's the instruction. Okay, we have the instruction. So we have the output here and the data here. So let's say I want to put 4002. I can put 4002 here and the output is here. So everything is still 32-bit. So it's still one instruction. So now the first instruction, move W, will put 0 here, okay, 0, 0, 0, 0. And then second instruction, move T is called move top. Okay, it will move the 16-bit number to the top part of the register. So we have 4002. Okay, so why didn't we teach this? It's because I didn't know. Okay, this is a new instruction only in term 2. And most of the new books still don't have this instruction in the books. Okay, somehow I found out last night. So now we can do this lah. We can use this. Okay, now what is 4002 0000? And this is only the starting address. So remember here, this is the first address. The first address from the block of registers. So from this block I can offset. So if I want to send data to ODR, I just offset 14. Or if I want to read data, I offset 10. So I can do that in one instruction because this is part of the addressing mode of ARM. So let's say I want to read data from IDR, I put LDR R1 R0. So R0 will have 4002 0000, and then we add 10. Okay. So now the effective address is 400 20010. So we will read data from the IDR into R1, right? Not using ADR instruction. Okay, this is so old-fashioned. No lah, can still use, but this is like something learned. I learned something new, and I excited to explain it to you. All right, and then if you want to send data out, let's say R2 contains something already. You want to send data to ODR. So we just put R0 here, which is 400 20,000, and then add 14. So I will send to this number lah. So it's offset. So R0 contain 420,000. The offset we put into the instruction. So you put 14 there in hexadecimal. Now we send data to location to the ODR. So basically these two examples are the same lah. So this one C in assembler, this second instruction also C converted to assembler.
Prof, but the IDR and ODR can only be either one, right? Since we configure the type in the mode R register, so it's either input output. So if it's configured as input, then we can only read value from IDR. Then ODR won't have logically won't have any value, right? And vice versa. If we configure output, then only value will be in ODR. IDR won't have anything. Is that correct assumption?
No. Let's say I will send data to LED. Okay. So let's say the port is output port.
Mhm.
Okay, the output port. Let me see. Not okay. I can read from ODR. I can read from ODR. So let's say I want to, I want to turn off an LED, but I don't want to change the others, right? So I read from the output port and I just modify one bit and I send it back to the output port. But yeah, you're correct. If the same register, then if you send to an output, you send data to an input port, then actually nothing happens. Okay, because
Okay.
you can mix input and output in the same port. So
Mm.
so if you send data to inputs, if you send data to switch, nothing happens lah. So no problem.
Ah.
You can use the same address.
But it's just that like no effect, right? If let's say if you configure it as an GPIO as an input, you configure from there and then you send the data to the ODR for GPIO, then it's like no effect, right?
No effect.
Okay.
And then default is input lah. So if you do STR to a register which is not configured, of course nothing happens. Yeah. So to turn on the LED on your blinker, you have to make sure it's output mode first. Then you can blink.
Okay.
By default is input. Right. So now we have shown how to access directly, which is not recommended lah because we play directly with the numbers and we tend to make mistakes lah if you put numbers like that. So what you do is you collect all the addresses in include file and use the include file. So of course lah, include file if corrupted, then what to do? But normally nothing, that thing doesn't happen lah. So for example, here I have my own file, 2 lines only. My STM32F446. I put these 2 lines. I put the define there. So GPIOA underscore IDR is defined as that long pointer. Okay, long pointer. So when I want to use, I just say val equal. Okay, so I just like this lah. I just do val equal GPIO ODR instead of all this. Okay, so that's dangerous because you can make a mistake. So here, less chance of mistake. We
Prof,
want to
the val variable is declared to be a pointer, is it?
no, it's an integer.
Okay.
Yeah, it's integer. Yeah, I should put I should add there also lah. Yeah, because the data is integer. The pointer is the address that you get the data from. Okay, so ouch. I put okay now I read from ODR and I send back to ODR. No problem. Okay, because let's say I have an LED, I have to read from the LED and modify one bit and I turn it back. So for example, to turn on Nucleo user LED, which is port A bit 5. So I have to find which is the location. So look at ODR. Okay, ODR is like this. Many bits. Okay, so bit 0, 1, 2, 3, 4. Okay, bit 5 means 5 here lah. Okay, so if I want to turn on only, then that means I have to use OR function lah. So take the register value or that bit. So in binary that will be 0, 0, 1, 0, 0, 0, 0, 0. So that's why we have hexadecimal 20 there. Because you want this bit to be 1, then the others don't touch the others. But this style not elegant lah. So for me I like this one better. So 1 shifted by 5. So I have 1 here, I shift left 5. I will still get 1, 0, 0. So basically this become 1, 0, 0, 0. 5 zeros at the back. 0, 0, 0, 0. Okay. 1 shifted left 5 times is equal to 1 followed by 5 zeros. Okay. So shortcut. Very easy. Okay. Clear lah how many bits you are shifting and also the same number is bit 5. Put 5 here. So I recommend you to use this method. It's up to you lah. You can use hexadecimal to make my life hell in the final. And I have to convert back to 0. Which bit is on, which bit is off. Susah juga lah, but No, it's not wrong. Okay, so now we go to maybe another method, but before that we have to add our knowledge on C. Yeah? So in C we have what's called the type def statement, which allow you to create a new data type, rename or actually create a new data type. So here we just rename, because what we do is alamak typo here. Type def integer weight. Okay, so what we do here is actually just rename integer to weight. So next time we declare weight data type is actually integer data type. So we have weight w1, w2. Okay, it's the same. Integer w1, w2 is the same, but because it's only a rename. But if you use type def with a struct at the same time, okay, you have to follow this format lah. Okay, type def struct and then open brace, close brace, and then the struct name. We can have a structure. Okay, a structure is like a block of data like that. So you have integer, you have age here, have height, and we have weight. Okay. So let's say I have John and Mary. So I will have two of these. Okay, I will have John, and also Mary will also have the other one. So the moment you declare record John and Mary, so I will have Mary age, Mary height, and Mary weight. Okay, so I have two structures like that. So now it's let's say I want to update John age to 22. I just say John age 22. So I will go to John structure and I will put 22 here. But of course, this one not yet. The others are not yet initialized lah. So by using this, we can go to age field inside the John structure, the record structure, label as John, and go there and update the variable. Okay, and then we use the dot. Okay, the dot notation. Okay, now to use this, we have to do some homework first lah. So if you use CMSIS or KEL, actually all these definitions are there already. Okay, we don't need to create our own include like this. Okay, but if of course this include is lighter lah. This include from KEL, they are quite long. They will slow down the compilation. But sometimes laziness override everything, right? Just use whatever is available. So inside the CMSIS header file or KEL header file, you already have this. The peripheral base, of course, is 40 million. Because all the peripherals start at 40 million. And then we have the peripheral base for APB1, APB2, HB1, HB2. And then for the GPIOA is the address is AHB1 peripheral base, which is AHB1. This one lah. Okay, so you have to add lah. So 440 million plus 20,000 plus euro. And then if you have other ports like if you want to access port B, C, D, or N, and so on, the base address will be different. Okay, so as I mentioned, these registers not relevant for our chip because they are not available. Till when you compile, you have to read in all this junk because you cannot remove this from the system header files. Okay, then next we create a type def for the registers. Because if you have a structure like this, you can create a pointer here and you can create an offset. So this is where the type def struct comes in. So we have the GPIO type def. So we put all these registers here in the proper order because they will not shuffle lah. So which one comes first will come first. So that means like if you put IDR here as number 5, it will always maintain the offset of 10 hex and so on. Right, okay, I typo here, so record there. Alright, so this is the type def for the block. So let's say I have GPIO, GPIOA. The first address will be 420. Okay, I have to count. Okay, then all the rest will be the structure members. So within the structure, I have what are first, okay, offset of 0. Then let's say I want to zoom into IDR somewhere down here, offset of 10. Okay, so GPIOA here, okay, going here. But if I apply the same to, if I want to do the same for GPIOC, for example, so the difference is only the base address. So GPIOC, let me see. If I see the base is off by 8, here instead of 0 is 8 for GPIOC. Yeah? So C is 400, 800. So only the first address need to be changed. So the offset, they're all the same. So that means for the IDR, okay, for knowing this, you can already calculate GPIOC ODR will be 42810. Okay, so this one is port C. Okay, for port C, all start with 8. 2 here is for GPIO. Anything with GPIO is start with 2 here. Port C is here, and then 10 here is for the IDR, and so on. Okay, of course, this is just for knowing what is the actual address. But if you have this type def, you don't have to know the actual address. You just use the labels. Okay, so knowing the labels, you can access immediately access lah. But because now you have type def and you have a pointer, so you use this particular syntax. Okay, type def is already defined. Okay, here type def struct GPIO underscore type def. So you just put there GPIO underscore type def star. So that becomes a pointer. I want to send GPIO ODR. I just do give this instruction. Okay, done. The data is sent. But this syntax or this format is quite common. This is quite common. So it's more normal or more elegant to use the arrow notation. So you put GPIOA arrow 0. So ouch. Typo. The one at the bottom is correct. It should be ODR equal 0. Then okay lah. Okay, so instead of bracket star GPIO bracket dot ODR, we put GPIO arrow ODR equal 0. So then this one is exactly the same. Alright, so if I want to turn off the LED on the Nucleo, I don't put 0 there, right? I cannot put 0. I must mask. I must get the data from ODR and then end it with 1, except for that bit that you want to clear, and you send it back. So this is the pattern lah. Okay, so this will generate tilde 1 shift left 5. So that will become 1111 1111 11 16 bit lah. 1 I think 5 is here. So 1101 1111. Okay, 1 2 3 4 5 6 7 8. Okay, so it's actually you are ending with, okay, what you're doing here to clear that bit. You have to do this GPIO A ODR end with X F F F F F F 1 2 3 4 5 6. This one is CD. Okay, D F. Okay, so who wants to do this? Huh? Nobody wants to do this. Okay, this is old style. Effect is the same. Okay, you end the ODR with FFFF, FFDF. You will clear bit 5. But don't do this, please. So this is the style. Okay, you put 1, shift 5, and invert. So you will get 1 at bit 5, and then you invert and you get this mask lah. FFFF, FDF. So this is the method to use. You can also use the third method. But why? Why you would want to do this? Or you can also use the top method using the first method. This one is this method. Okay, using the direct register without the structure. Okay. So this one doesn't use a structure. It's hard coded lah. So GPIO A underscore ODR is a number. A number is already calculated. To use this arrow notation, you must have a type def. Okay. So any questions so far? Short break lah. I have to drink something. Okay, no questions. Then I short break. Another short break.
Yes,
You.
still here.
Yeah, cool over there. Okay, so let's continue. Okay, actually we are halfway through the notes lah. I have 70 pages, so now we are page 35. Time is also about halfway through, so it should be done by on time. Okay. All right. So here is the plan. If you want to use anything, if you want to if you want to use the I/O port on ARM on STM32, you cannot just go ahead and do it like in AVR or PIC or whatever lah, right? Well, most of the microcontrollers, I think they default on output. The ports are default to output. So if you want to create a blinky, you just write the blinky code. You don't have to do anything. Okay, so if you need 5 instructions to do blinking, okay, your first program will be that 5 instructions, and there's nothing to configure. But on the ARM, no, you cannot do that. There's clocks there that you have to know. Okay, so you have to know which one you want to use. Is it a local clock, internal clock, external clock? Are you going to reprogram the PLL? Okay, and then you have to know the frequency. Okay, and then you have to enable the clock to the GPIO. Okay, if you don't enable the clock to GPIO, you cannot use the GPIO. So let's say I assume this one no problem. I still have to do this. Okay, so I still have to know a bit about clocks. Then I can enable the GPIO. Then I can use the GPIO. Okay, so if I use the GPIO, maybe I want to use not the GPIO. No, the enable the GPIO means I use that particular port. For example, port A. So port A can do GPIO by default, but can also do other alternate functions. So if, for example, I'm not sure lah, GPIO I didn't check. What can GPIO A do? What can port A do instead of just general purpose IO? Have to check the documentation. So if I want to use it for something other than GPIO, then I have to enable the other clocks also. Okay, and then I have to configure the alternate functions. But if I just want to use for GPIO, then I skip that part. Okay, so you have to configure the GPIO if you want to use for output. Okay, for input no need input no need. And then if I want to use interrupt, I have to program the NPIC interrupt controller. Okay, so this one not yet lah. We're still in the program IO, or the simplest type of IO. All right, so let's say I want to enable the clock. So how do I do it? So this register and enable the port. Okay, so if I want to use port A, I have to turn on. I have to put 1 here. Okay, so to do that, I give this instruction: RCC underscore AHB 1 ENR or 1. So 1 is easy lah, just put in 1. But if I want to use, for example, port H, so of course I will do this lah. I will do, instead of this, I will replace this with 1 left shift 7. Okay, in case I want to enable GPIO port H. Right, and then the others, a lot of reserve there. No need to worry about. Okay, just turn on the bit that you want, but you still have to do this. Otherwise, you cannot use the GPIO. And then for the GPIO, each bit has to be it have to set the direction. Okay, so let's say I want to put I want to use the LED on the Nucleo. So that will be GPIO-A mode R. GPIO-A mode R, where here I put A instead of X, and X here can be A to H. Okay, so reset value for port A is A8. So what does it mean? 1 0 1 0 1 0 0 0, and all the rest are zeros. Okay, so that means what does it mean? It means that 1 0 here. Okay, this 1 0 here, this is for setting the mode for bit number 15. So bit number 15 is alternate function. Bit number 14 is also alternate function. Same thing with bit number 13. Okay, see this number here. Okay, so that is this 2-bit control. This 2-bit pair control each bit pair control 1 bit or one pin. So this is so you should not change this line because this is the default value. So let's say I just want to turn on the LED on the nuclear board. So I will have to find out which bit, and the bit is bit 5, right? So LED on the nuclear is PA5. So PA5 means I have to go to this bit pair. And by default is input. So I don't want that. I want to make it output. So I have to put 0, 1. So 0, 1. I have to put 0, 1 here. So I put basically I have to put 1 in bit 10 and leave all the others unchanged. So I have the solution. I have the solution here, but I will explain here lah. So if I just want to turn on the LED or make it output, so I will do this lah. So GPIO PA underscore mode or arrow if arrow mode R, and then I put OR, and then I want to turn on bit 10 only, so I put 1 left shift 10. Okay, brackets are optional. Okay, then after this the pin is configured for output. So the rest don't touch. So to do that, you put OR function. Okay, and then to send data, you use the output data register. So in this case, 1 bit, 1 pin, and port A, all the ports they go up to 16-bit only, even though the data size or this register it uses 32-bit, but only the lower 16-bit is used. Okay, so unused space, so don't touch lah. There's nothing that happens if you send data there. All right, so to control the LED, that means first you have to turn on the port, okay, enable the clock. So we've seen this before just now here, okay, turn on 1. Okay, this one should be improved. Use RCC arrow and turn on bit 1, and then bit 10 I put on turn on 1 so that bit PA5 become output mode, and then I do the loop lah. So in this loop I just toggle this bit. So GPIO will fall again. So it should be GPIO A, ODR, and then toggle this bit, toggle bit 5. And this number here I got from this document. I didn't check. So anybody of you who've got free time later, please test for me. So basically this is the minimum, the shortest code that you can run on the KEL. When you don't use STM32, just go ahead, delete everything that STM32 give you and paste this code. Maybe it will work. I have not tested it, but I just copied from this PDF file. So this paper, this document say if you put 3195, it will be equivalent to 1 millisecond. Okay, on 16 megahertz. Okay, 60 megahertz, which is default because I didn't change anything. Okay? On default is 16 megahertz, right? So I didn't change any clock, and whatever. So the processor will run at 60 megahertz. So at 60 megahertz, 3195 is 1 millisecond. If I want 500 millisecond, I put times 500. Then I just make this loop. This is the delay loop. Okay, so this LED will turn on at 1 hertz lah. Okay, because 500 millisecond high, then I toggle after that. So it will be 500 milliseconds, I think. Okay. Theory is there. The number, the exact number is to be tested for you or by you guys. Since you are doing your assignment, you can check it out for me. Okay, if not, blame this guy, whoever this guy is to make the notes. But it should work lah. Okay. Alright, so if for input, you go to the IDR. Again, there's up to port H, and on our chip, not all ports are available. And for same like the ODR, there's 32 bits available, or you can read 32 bits, but only the 16 lower bits are useful. So now, let's say I want to read the switch. The switch is on, remember on the video, switch is on PC13, if I'm not mistaken. Okay, so now I enable the clock for both A and C. So I have to put 3 here. Okay, remember where is it? Okay, here. I want to enable port C and A. Okay? 101. Typo. Okay, should be 5. Okay, should be 5, not 3. Okay, 5 there. Okay, to enable port A and C, I should put 5 there, and then I send 400 to board register to make port PA5 output. Let me check again. Is it 500? Is it 400? This one. This one. Okay, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, 0, 0, 4. Yeah, 400. Okay, 400 here. Of course, this one is just looking for trouble doing hexadecimal. I could have done one like that just now. It's easier. But just to show lah, the alternatives. This method still works, except that debugging is crazy lah. Okay, so I read the switch. Okay, so I read the switch from GPIOC IDR, and I immediately mask it. So I read the data. Okay, this expression will read the whole port C, but I want to only look at bit 13. Okay, bit 13. So this is the mask. Again, dangerous. I'm not sure. I try my best lah. I think this is bit 13. So actually should be and 1 shifted 13 times. This one easier, that you know you are looking at bit 13. So take this value from GPIOC IDR, end it with 100,000. So what is the value here? What is the possible values? Anybody can answer? What are the possible values for swing? Swing, well, what? Hey, everybody sleeping.
One also.
What's that?
0 or 1.
Not 0 or 1. 0 or possible to get 0, but what's the other value?
1 0 0 0 0 hex.
The value lah. That value. Or 0x 100,000. 100,000. Okay. Now, what does it mean? What this mean? What this means? Okay. What does 0 mean? Assume that you press the button, become 1. Okay, so I'm not sure. Okay, I didn't do it myself. So this one, assume press, I get logic high. Press, I get high on the pin. So what happened here if I press the button? Do I get 0 or do I get 100,000? Should be this one lah, right? So are you going to check? Are you going to check this value? How do you easily check this value? So this is the way to do it. Okay, because in C, 0 is false. Anything non-zero is true. So it doesn't matter what is the exact value, as long as it's non-zero, it's true. Okay, so I just put if swing. So if swing is non-zero, I will execute this line. If 0 only, will execute second line. And then we can turn the LED on or off. Alright, so this one, another program I just copy from this website. Of course, I didn't test it. Okay, I admit that, but looks like it made sense. Okay, what's the difference between this one and the previous one? Okay, here, what this program is trying to do is to toggle the bit as fast as possible. Okay, so you must change the clock. So to do that, you have to initialize the clock, and there's another subroutine here, a function here. Okay, so a lot of things. I'm not sure. I don't think that even the website, I don't think it explains everything. But basically, you have to manipulate a lot of bits. Okay, a lot of bits. Then you can get the maximum speed. Okay, so get the maximum speed. So if you only rely on the built-in RC oscillator, you can only get 160 megahertz using the PLL and the VCO, whatever. That's the best you can get free if you don't put a crystal outside. If you want to get 180, you put the crystal outside. So we get the speed, high speed. Okay, change the speed from 60 megahertz to 60 megahertz. We upgrade to 168. Okay. Now after we change the clock, then we do the same thing as the last time. So enable the clock to the register, and then set the bit to output, and then change the speed. Okay, this is new. Okay, so we want to go high speed. We go to this register. Okay, not covered before. So for this one, you can always look at the manual. And then there's also another register, PUPDR. Okay, we'll see later, but not relevant for output. Okay, and then here we just toggle, and no delay. So send high or low as soon as possible. So this is the fastest loop that we can get. Okay, so that means it's also possible that the STM cube, okay, also do this, and we don't care normally. Okay, so when you use STM cube MX, will do a lot of configuration, and they put in the function. And as a programmer or as a engineer, these are the too much detail that we don't need to know. Okay, we just want the processor to run at whatever speed, and let the configuration tool set all the bits. Okay, but this particular person, this guy, he hacked everything lah. So if you want to know the detail, you go to that website. Okay, and then we have another register. Instead of ODR or IDR, we can also do bit set or reset. So in this case, we can set or reset without reading and writing. Okay, let's say I want to turn on LED at pin 5. I just put 1 here, and if I want to turn off, I put 1 here. Okay, for reset, put 1 in the BR5. For set, I put 1 here. So you just put 1 there. And this register is writing, that write only. So that's why they put www here. You can only write to this register, and reading this register doesn't have any meaning. So for our LED, for example, we can set all that, and then to turn on the LED, you put 1 here. So I will get 0, 0, 0, 0, 0, 0, 1 0 here. So this is 2 0. So to set the bit, I put 20 hex. So turn on LED on the nucleo with port 5. And then we put the delay, and again here multiple of the delay here is programmable, multiple of milliseconds. Okay, anyway, going back here, okay, turn on the LED, delay for 500 milliseconds, and to turn off, you go 20 also, but shifted by half word. So 20, this 20 here is lower half word, here is the upper half word. So that means it will go to the top one. So we'll get 0, 1, 0, 0. So we'll get 2 0, and then followed by 4 zeros after that. Okay, and then you can also do it the way that you've done so far, okay, by using the HAL. So the HAL, the hardware abstraction layer, comes from ST Microelectronic. Okay? So this one could not, maybe it's possible that I think it will not work if you use another chip from another company. So the purpose of HAL is to make it a lot easier to migrate between microcontroller if needed. If you have no plan to migrate, actually HAL may be useful a little bit yeah, to look at the register at a high level. But there's if you don't plan to migrate, the advantage is not so big lah. Because there's also disadvantage of HAL. It's convoluted. Convoluted means what? Berbelit-belit lah. Jump here and there, and then the code is sometimes not efficient. Okay, also there's lack of documentation, lack of clean example code, not much example code for your hardware. So you have to use example for different kind of processor maybe, and try if it works on your processor. And HAL is always updated because it's still new. Okay, not it's less than 10 years old. It's quite new in microprocessor. That less than 10 years is quite new. So still work in progress, and they still update. So if you update, then some functions may not work anymore. But I will imagine for GPIO no problem lah. GPIO is quite standard and nothing much change. Okay, so the syntax is if HAL in front, that means it's a function. There's one space, and then followed by HAL is a macro, and then there's two types of macro there. Okay, so if you use your own software, it will be like this. Okay, it's a snippet. Snippet is a useful sequence of code that you share. Okay, so normally this snippet they are device specific. You can only use for one device, and it's not portable. And it's possible that you also have some libraries from last time. Okay, and then now ST Micro, they try to merge all this. They want to upgrade to the abstraction software. So for the abstraction, there's 3 layers. There's the middleware, there's the HAL, and then the low level API. So the low level is the one that is really doing the work, and well, maybe GPIO should be quite efficient because for GPIO there's nothing else to explore. So when you install the HAL, you have to make sure you have all this, then you can generate the proper code. Okay, so if you look in the CMSIS architecture, this is your code. Okay, as you have put there, SRC folder, and then have the CMSIs folder. And if you are not using CMSIs, for example, you will not have anything there, but the hull will be this purplish color here. Okay, so it will be this area, and then if you're doing simple blinky, it will go here, and then go to your CPU lah. Okay, so the path is shorter. But if you have, like, if you want to use file system, okay, if you want to use RTOS or DSP, of course you have to make sure they're all linked together. Okay, so HAL is on this side. Okay, CMSIS is on the left side. So CMSIS is the green one is ARM, so more stable. The HAL is from ST. So this one is the one that we're talking about the stability. Not so sure yet for long term. So this is the mapping of where everything goes through. Okay, so this is what happens if you take the STM Cube software and you delete out all the comments. So you have only 3 configuration lines, and then to write you use HAL GPIO write pin, and you have HAL delay, and then to reset also you use the same function. Okay, so it looks easier, but I'm not sure about you. For me, it takes longer to type lah, because the text are there's a lot of text to key in. Okay, so any questions so far? How to make sure CMC is linked? When you call it, there's no error. So CMC has the header file. They have headers have what? Special names, right? So you can identify which one is CMCs. Okay, so if you call the function and there's no error, then mean okay on the link. If you call and there's an error, that means it's not properly linked. Okay, so let's move on. There are 20 more slides only. Okay, so now we go to output interfacing. So this one is the hardware side. And just now this was the software side. Okay, so in a digital circuit, signal lines should not be allowed to float. Okay, so if for some CMOS circuits, if you float the uh, gate, they will short, okay, and damage the system, damage the circuit, especially the old CMOS chip. Nowadays they have some protection, but the old one, it's possible to break. And then also, if you float, you do not know what is the value of the input. So you must put it to high state or low state. If you float, then the state is undetermined. You do not know whether it's 0 or 1. In TTL, no problem. TTL for floating input, they go to 1. But CMOS, you do not know. And they also can have the reliability problem later on. So the correct way to do this is to add a resistor to either VCC or ground, so that you pull up the voltage or pull down the voltage. Right, so if the line is not actively driven, okay, there's no input, no connection from another output. Okay. For example, here I have inverter. Okay, it's floating just like that. So what is this value? Is it 0? Is it 1? So what's the output here? Is it 1? Or is it 0? We do not know because the input is floating. So we put if we put a resistor, and then there's a switch at the back, and if the switch is not pressed, then we know it will get 1. So in microcontroller, the job of the resistor is by the NMOS or PMOS transistor. So and then for STM, we have to configure the GPIO board. Okay, for output, we have to choose whether it's totem pole, okay, or open drain. Open drain here means that the output can only go down. Okay, for example, I have okay, if this transistor is on, so that means in front will have leakage current going back. It can go to down. But what if, okay, this is when I put one here lah. If I put one here, this transistor will turn on, so there will be a short, so I will get 0 here. But what if I put 0 here? Put 0 here, this transistor will be off, right? Will be off. So it will float here because it's like open circuit, so it will float. So if you connect this to another output, this is no good. But if I want to use this kind of output to LED, no problem. So if I have an LED, I put a resistor here. So if I turn this on, I will have current. So the LED will turn on. If I turn off the transistor, there's no current flowing, the LED will turn off. So it's okay for output interfacing. This floating, it looks like it's floating, but it's okay because you only need to turn on when you need to have a current, and when there's no current to LED, the LED will turn off. So the open drain is only for output, not for input. So it can pull the pin towards ground. So this pin can go to ground, so it can go ground, but it cannot drive high because the high is caused by the VCC here. Okay, so for this type of output, there needs to be a pull-up resistor. Okay, so this is the pull-up resistor. Okay, so to choose whether you want to have push-pull or open drain, you set the resistor here. So output push-pull is reset the default, and open drain is selectable. If you want open drain, you can make it open drain by putting 1 at the proper bits. And the other one is for input. Okay, for input, you can select whether you want to have pull up, pull down. and no pull up, pull down, okay, or you can choose whether it's pull up only or pull down only. Okay, so and next we, since I've shown you the LED, so let's say we want to interface with LED. There are things that you have to consider. So one is the voltage drop. If you put an LED, there's a voltage drop here. So depending on the LED, let's say I choose the smallest one, maybe 1.6 volt drop here. So that means if I have 3.3 volt here, there's a voltage drop of 1.6 here. So that means voltage here will be 1.7. Okay. Assuming that if I put ground here, we turn on. So if you put ground here, we'll have current. So 3.3 volt here, ground here. So constant 1.7. So the voltage at the bottom of the resistor will be 1.7 volts. So this one is constant, the 1.7. Whenever we have current flow, if you put logic 1 here, of course there's no current, then this voltage will be also floating. Okay, so to turn on LED, there's two ways. One is using negative logic. Right? The first way is negative logic. On when port is low. So when you put low here, current flows to the ground or to the input port, and you turn on the LED. The other one is on when port is high. So when we put high here, the current flows to ground. Okay, so for TTL, previously we only have this one. They don't allow the second method. But now many microcontroller has good output current, and they allow the second type, but make sure your LED is a high efficiency or the one that doesn't require so much current, because the current here is limited. So if the LED is small, no problem, but if you have a big LED which have high current requirement, you have to choose method number one. Okay, so let's say I want to do Night Rider. So you know Night Rider, right? Night Rider is one LED on and the others off. So it's like this. Let me see. 8, 0. Okay. 1, 0, 0, 0, 0, 0, 0. And then I have like this. Next, I have, and so on. Okay, so it will recycle, it will repeat. Okay, so this is 8, 0 hex, 4, 0 hex, 2, 0 hex, 1, 0 hex. Continue 0, 8, 0, 4, 0, 2, 0, 1, and continue. So if you keep on doing this, you will see the lights running. Okay, it's also the running light. Okay, so just put this number in a table like this. Okay, actually this is the lazy way to do it lah, or the one way, only one way to do it, right, is by using a table. But if you use a table, you can have any pattern that you like. Of course, you can also do bit shifting. So enable the clock, and then make all the ports output. Send output from the table. Okay, pick a value from the table. Pick a value from the table. So first you put 80. Okay, so it will replace here. And then we have to do this fancy stuff here because we don't want to change all the other bits. So you take this value from the table, replace this expression, or it with this thing. So if your register is large like that, so this one you don't touch. Okay, so this one not touch. You only modify this last. So that's why we have this FFF. Want to keep the whole value. Okay, you only update the second byte. Okay, this is 2 bytes here. So here maybe 80. Okay, so 2 bytes here. And just keep on replacing this and at the output you can see some running light. Okay, so if running light is not interesting, then you try to use 7-segment display. So 7 display, you can display decimal, or you can also do uh, some extra work to make it hexadecimal. So there's two types, common anode and common cathode. So for common anode, the output is high, the LED is on when the output is low. It's like this. I don't have the diagram. You put a resistor here. Okay, this is your microprocessor, microcontroller. You have many, we have seven resistor, and anode is here. So common anode is actually the VDD. Okay. So if you put 0 here, current will flow through the segment and go back to the input, and you'll turn on the segment. If you have common cathode, then it will go the other way. Okay, so the common cathode is here. This is the ground is the common cathode. So you put one here, current will flow and turn on the LED. This diagram that I have, this table is like that I have is for common cathode, because if I want to put 0 here, if I want to put 0, I need to turn on segment A, B, C, D, E, F. Okay, A, B, C, D, E, F is 1. I will put 0. I will show 0 there, and so on. Okay, so you can do some exercise. So make sure you do this. Nobody's going to check on you. Possible it will come out in test 2. So test 2 maybe next week or 2 weeks time. So we will have test 2, and maybe we'll ask one of these 4 questions maybe. So you can write decimal C code to show decimal value which is incremented by 1 every second. So I basically 0, 1, 2, 3, 4 until 9, and then I will restart 0, 1, 2, 3, so on. Okay, and then you can modify this code so that it will show hexadecimal value. So 0 to 9, and then A to F, and then go back to 0. Or you can make one segment light up in circular clockwise pattern. Or you can modify the light so that to go back and forth. If I go run back and forth. Okay, so that is your exercise. And then we have, you can also connect the 7 segment through a 7 segment decoder driver. So in this case, you only send BCD code, and the BCD code will convert the BCD number to the digit 0 to 9. Okay, after 9, the number is kind of random, and then if you send 1111, the display is completely blank. I've shown some calculation here for the resistor, how much resistor you need. Okay, assuming the voltage drop across the LED is 1.5. So I didn't put it here because no space. Put it here. It's same idea lah. Okay, anytime you have a resistor and LED, you must put a resistor, and you have to do some rough estimation on the resistor value. This resistor value doesn't have to be exact, because the LED can tolerate some variation, but not too much. Okay, and then we can also connect, let's say I want to have 4 digits. I need 4 7-segment display connected to 4 digits. So this is the easiest and the laziest lah. So let's say I want to send number 1, 2, 3, 4. Okay, and then the display is connected to PA5. PA PA, not PA5, PA15 to PA0. Okay, so it's quite easy lah. Just send the data to the ODR. Okay, you will see 1, 2, 3, 4, and this data is already in hexadecimal. But what if the data is, what is the variable our data is 1, 2, 3, 4 decimal? Okay, so let's think about it. What do you need to do? Here is hexadecimal. What if this is decimal? If you send the data directly, what will happen? How are you going to change it to hexadecimal? All right, and then this method, okay, is not common because the cost of the 7-segment display driver is it costs money lah. So if you want to make it cheap, you go to multiplex method. So using multiplexing, you only spend one transistor. Okay, you need to have one transistor and one resistor for each digit, and then you have the digit itself. But you don't need the driver, and you can connect the 7-segment directly from the processor. So multiplex means only one digit is turned on at one time, and you cycle. You turn on digit 1, and then digit 2, and then digit 3, and you switch between them very quickly. This is what happened in your old TV. The analog TV also works like this, but the scanning is very fast. So it's very fast. If it's fast enough, you cannot see it switching, but cannot be too fast. For LED, it cannot be too fast because the current will not be enough to turn on the LED. So you must be slow, like around 25 hertz or 50 hertz. Okay, you have to update the value, or you have to light up at least 50 times a second, and not more. Okay, not more than 50. If you make the refresh rate too high, then the LED doesn't have enough brightness. Okay, so this one, you can see the code here. Okay, you can click here and you can see how they do it for these three digits. Okay, so last section, okay, only a few more slides, then we can have lunch. Okay, so now we try to interface with input switches. So for switch, we also have the choice of active high or active low. So active high here means that if you press, you will see 1. If you don't press, you will see 0. Okay, active low is press, you see 0. Okay, so the diagram here is for active low. Okay, so what happened here? The MCU is over here. Okay, the controller is over here. So if I press here, so the value will be 0. If I don't press, I will have 1 here, because there's the value cannot go to ground, and through a resistor actually there's not much, so actually it should be here. So this is active low. Press become 0, no press become 1. And then here the capacitor here is for the bouncing, so that you don't have so much glitch. Okay, so nowadays, because of CMOS, you can have symmetrical high and low. So you can also do this type now. Okay. So if you press, you will get VCC. Okay, you press, get VCC. If you don't press, you get 0. For TTL, this is for TTL. A long time ago, this is the only method you can use. Now you can also use the bottom method, but you can still use the top method if you want. Okay, so normally the switches you can have single switches like the one on the nucleo, or you can have deep switches. So the deep switches, they put everything in the deep package, and you probably find this when you have you need to configure something. So you can read all the data from the switch and do masking. So let's say only the lowest 8-bit is useful. So you read IDR like that, and you don't care about the rest. You only need the lowest 8-bit. So bit 0 to 7 only useful. So you have to mask it. So this is what happened here. You only keep the lower 8-bit and ignore the remaining bits. But you still have to read the whole port in one step. Okay, so almost the last slide. Okay, so if you have a push button, there is a problem of bouncing. Okay? So you press a button, there is input bounce about maybe 10 milliseconds or so, depending on the quality of the switch. If the switch is high quality, the bouncing is less, or maybe no bounce. But if a very cheap switch, maybe longer than 10 milliseconds. Okay, so this one, the bouncing can cause error in your program. So you must remove the bouncing. So you must convert that to a clean transition like that. So to do that, you can do hardware method. So hardware method, the best one is to use set reset latch. This is the number one method, but expensive. You can also do it cheaper using CMOS special debouncer, slightly cheaper, but the cheapest is just to use RC debouncer. So I think your switch and the nuclear board already have debouncing, so you will not have this problem. If you still have this problem, it will be much less. But if you create your own board, you need to have the consideration which method you want to use. Okay. Still, some people they say, oh, capacitor is still too expensive. So if you don't want to spend money on capacitor, then you do it software way. So what you do is you sample the data. If you see the data is 0, you wait 10 milliseconds. Okay, wait 10 milliseconds and you sample the data again. If it's 0 again, that means it's confirmed to be 0 lah. Because if the bounce is bad, for example, you do it like this, more than 10 milliseconds. You do it, sample first time is 0, you wait for 10 milliseconds, it's 1. Okay, you cancel. Okay, then sample again, start from here lah. So now this becomes the first sample of the second try, and then from there you check again from 10 milliseconds this time, you get 0. So you will get your correct report here lah. So this is maybe the same keystroke, but you will take a slightly longer to verify the key press because when you check it again like after 10 milliseconds, it's still high. So you reset everything. So you start scanning from here. When you get 0 here, from there, from the second 0 here, you go 10 milliseconds and sample again. So now from here is confirmed to be 0, then you do whatever you have to do. Okay. I think that's it for today. For this morning. So afternoon, Dr. Osman will take over. Okay, so that's it. Class dismissed.
So afternoon will be at 2 o'clock at my link.